Our second example is to talk about the moment of inertia and x double bar and y double bar for a surface that is a right angle triangle. So I'm going to first draw the integration region, which we have said that is a right angle triangle, and let's call this side is the base B and say this side is the height h. So recall one thing, then this point over here is b comma 0 and this point being the y-intercept is 0 comma h. So the equation of this oblique straight line is x over b plus y over h is equal to 1. We need this expression in order to find the limits for x and y. So let's solve it for y, and we will get y over h is equal to 1 minus x over b, which is equal to b minus x over b. And that means y is equal to h over b times b minus x. Why I did it, now you can ask yourself, what are the limits of the integration? So think about, I can integrate with respect to x first, and I will be integrating from the value of 0, x equal to 0, to all the way to this point x, which is going to be the x solution of this straight line. Because I have solved it for y, so let's go ahead and start doing integration with respect to y first, and it will be pretty similar approach. So we're going to go ahead and say that we will start our antiderivative with respect to y first, and so we start at y equal to 0 and go all the way to the hypotenuse. And remember that y value here is h over b times b minus x. So that is going to give you the limits for y. Whereas the limits for x is going to be the lowest value x equal to 0 to the highest value x equal to b. So let's write our antiderivative for the mass function. It's going to be limit of x, limit of y, which is again h over b times b minus x. Remember the density function is just 1. dy dx. So let's start working on the antiderivatives. So first you get integration 0 to b, antiderivative of 1 is y, then I'm going to put in the limits, and these are 0 to h over b times b minus x dx. So I get antiderivative 0 to b, h over b is the constant which I can pull out and do the antiderivative. So I get h over b. Antiderivative of b is going to be bx, and antiderivative of minus x is going to be minus x squared over 2. And now finally I'm going to put the limits in, which are 0 to b. So what we get, simplifying these, we will get the mass equal to h over b times, if I put in the upper limit, I get b times b squared minus b squared over 2. 0 doesn't contribute anything, so you get h over b times b squared over 2, which is bh over 2. And remember, this is the area of a right angle triangle just by the formula. We just evaluated the same formula using the several variable integration. So now your objective is to find the moment of inertia with respect to the x-axis, which is integration 0 to b, integration 0 to h over b times b minus x, and this time you're integrating y squared times the density function with respect to y first and then with respect to x. So when you get y cubed over 3, that's the antiderivative, then I have to take care of the limits. So h over b times b minus x dx. So put in the limit. Remember, 1/3 is a constant. I will take it out. What else is going to be a constant? When you put h over b in place of y, you get h to the power 3 over b to the power 3. That I will take out, 0 to b. And inside I will have b minus x whole to the power 3 dx. That's a pretty simple antiderivative. You can use chain rule or integration by parts, but I am just going to simply say that this is h cubed over 3b cubed. The antiderivative is b minus x whole to the power 4 over negative 4. Limits are 0 to b. So I'm going to now put in the limits. So when I put in x equal to b, I get 0. So I can first call it as h cubed over 3b cubed. And if you multiply 3 and 4, I can make it even looking better as 12b cubed. So let's go ahead and do that. And then, as I said, put x equal to b, you get b minus b, 0 to the power 4, 0. When you put x equal to 0, you get minus b to the power 4. So eventually I'm going to get minus times minus is a plus. So h cubed b to the power 4 over 12b cubed, which after simplification will give you hb over 12. So that's the moment of inertia with respect to the x-axis. What's next? We're going to find out the moment of inertia with respect to y-axis. So that will be integration 0 to b, 0 to h over b times b minus x. And this time you're integrating x squared times the density function 1 dy dx. So again, we will integrate with respect to y first, and when we do the integration with respect to y first, we're going to get 0 to b, x squared times y with the limits of 0 to h over b times b minus x dx. So we will get h over b again is a constant, I can pull it out. And I will have antiderivative of 0 to b. See this x squared term, I'm going to distribute over this b minus x term. So I will get bx squared minus x to the power 3 dx. And then we're going to simplify this antiderivative. So h over b times, let's do the antiderivative of bx squared. You get bx to the power 3 over 3 minus x to the power 4 over 4. And you have the limits of 0 to b. So I get h over b times, when I put in the upper limit, I get b to the power 4 over 3 minus b to the power 4 over 4. If I put 0, I don't get anything. And this is the term that we're going to simplify. So we will get h times b to the power 4 over b times 1/3 minus 1/4. So I'm going to write it as 4 over 12 minus 3 over 12. And that's 1 over 12. And then cancel one of the b's. You get h b to the power 3 over 12. As your answer to the end question. So essentially, and oh, I actually forgot the h to the power 3 here, so I'm going to go ahead and put in the h to the power 3. So I got the ix, I got the iy, and I got the mass, which is bh over 2. And we are going to compute all this information in terms of finding x double bar and y double bar. Remember, x double bar is square root of iy over m, and iy we found out is h b to the power 3 over 3, and I'm dividing it by hb over 2. So what I get 2b squared over 3 square root of that. So this is b square root of 2 over 3. And you can call it b square root of 6 over 3 by rationalizing the denominator. So that's x double bar. Let's find out y double bar. So that's going to be square root of ix over m, which is square root of, well, ix was h cubed b over 12. That's your ix, h cubed b over 12, all over the mass hb over 2. So this is going to be h cubed b over 12 times 2 over HB, and then we are going to do all our cancellations, possible cancellations, and we will get, so 2 cancels this thing, and you get a 6. So you get 8 squared over 6, and I think I made one more mistake in this problem. I'm so sorry, I'm keep making mistakes. So this is going to be 8 squared of 6 over 6. So remember when I was writing IY, I wrote 3 for some reason. That should have been a 12 on the top. I'm so sorry for this confusion. So that should have been HB cubed over 12. And this turns out to be, after simplification, b squared over 6. So that should be square root of 1 over 6. And then I can simplify it as b square root of 6 over 6. And that would answer your question for finding x double bar and y double bar.